Hello, my name is Shahriari, and this is a lecture in a series of lectures on undergraduate abstract algebra. This particular lecture is on subrings and their identities. It's a particularly short lecture. This is all based on, the whole series of lectures are based on my book, Algebra in Action, A Course in Groups, Rings, and Fields. So let's get started. So let's recall the definition of rings. So a ring is a set, an abstract set with unidentified elements that has two operations on it. We have something that we call plus and something that we call multiplication. With plus, we have an abelian group. So we have closure. If you add two elements, you get something in the ring. You have associativity. A plus B plus C is the same as A plus B plus C. You have a additive identity, which we denote by 0. A plus 0 is 0. And we also have commutativity. That's why it's kind of abelian group. A plus B equals B plus A. We also have additive inverses. For every element A, there is a minus A, that when you add A to minus A, you will get that 0 element. With multiplication, we ask a lot less. We only have closure. If you multiply two elements, you get an element in your set. And associativity. AB times C is the same as A times BC. We also have distributive laws that connect the two things. A times B plus C is AB plus AC, and B plus C times A is BA plus CA. The additive identity of this ring is denoted by 0. And in fact, we don't call it identity, we call it the 0. So the 0 of the ring is the additive identity, is the guy that when you add to other things, you get that thing back again. If the ring has a multiplicative identity, then it's called a ring with identity. In that case, that multiplicative identity is denoted by 1. So in an identity in a ring, we usually are thinking about the multiplicative identity, which may or may not be there, and we call it a 1. The additive identity we usually call 0. Now, the purpose of this lecture is to talk about subrings, so I'm going to define them. And the reason this lecture is short is because unlike groups where subgroups play an outsized role in the theory, subrings play less of a role. They do play a role, but less of a role. But the corresponding thing to normal subgroups, which are ideals, play a very big role. And those are the subject of the next video. So let's say you have a ring, and this definition is not going to surprise you. If you have a non-empty subset of that ring, then it's a subring if it itself, with the same operations, the same plus and the multiplication of the bigger ring, is also a ring. And it's not hard to see that if you have a ring and if you have a non-empty subset, then what do you have to check to make sure that it is a subring? Some properties it inherits from the big ring. Like, for example, the multiplication is going to be associative. The addition is going to be associative because they're already associative in the bigger ring, and this is the same operations. And so those things we do not need to check. Or addition is going to be commutative. We don't have to check that. All we have to check is to check that S is a subring of R, is that for that it's closed under addition and multiplication. So if you take two elements, S1 and S2 in S, S1 plus S2 and S1, S2 is R in S, and also that for every for all S in S minus S is in S. If for all S in S minus S in S, and S is non-empty, then you take that one element that you know is in S, add it to this negative because it's going to be also closed under addition, then you know that the 0 will be there. And so, for example, you don't have to check that the 0 element is there. So this is all you need to check. And another way of saying that is that a non-empty subset is a subring if and only if it's closed under addition, multiplication, and subtraction. Okay, some examples. So the integers are a subset, but also a subring of the rationals. The rationals are a subring of the real numbers, and the integers, therefore, is also a subring of the real numbers, and the real numbers are a subring of the complex numbers. Here's another example. If you take the ring of 2x2 matrices with integer entries and then look at diagonal matrices, then these are diagonal matrices with integer entries, then S is a subset of R, but more than that, it's closed under addition. If you add two diagonal matrices, you get another diagonal matrix. If you multiply two diagonal matrices, you still get a diagonal matrix. And if you subtract two diagonal matrices, you still will have a diagonal matrix. And so it's a subring of R. Here's another example. If you take the ring of polynomials with real coefficients, so the elements of R are polynomials that you can make, but you use real numbers as the coefficients. And then you look at those of them where the constant term is even. So 0, 2, 4, 6, -2, -8, and so forth. So as long as the constant term is even, then that will be a subring also, because if you take two polynomials which have even constant term and add them, the even plus even is even, so that the constant term of the resultant thing will also be even. Same thing with multiplication and subtraction. Okay, now let's think about the 0 and the 1 of subrings. I mean, that's actually the little note that I want to make in this short lecture. So if you have that S is a subring of R, then with addition, S is actually a subgroup of the abelian group R. And in subgroups, always identities are shared. Subgroups have exactly the same identity as the big group. And so 0, which is the additive identity of S, is going to be the same as 0 of S is going to be the same as 0 of R. The 0 is never going to be different. The argument for this is actually not that difficult. You may remember this from group theory, but if you don't, here it is. If you pick any elements of S, and S is non-empty if it's a subring, and that X could be just the 0 of S, for example, then we know that the 0 of S plus X equals X. That's the property of 0, that if you add it, nothing will happen. But this statement, 0S plus X equals X, is also a statement about elements of R, the bigger ring. And in that bigger ring, what we can do is we can add minus X to both sides. So we're now doing that in the bigger ring because every element X has a negative. Okay, then what we're going to do is we're going to say, what's X minus X? Well, in the bigger ring R, we're now thinking of bigger ring R. If you take an element minus X, you're going to get 0 of R. And on the left-hand side, if you use distributive law and you say 0S plus X minus X, that X minus X is also 0 of R, and 0 of S plus 0 of R is 0 of S, because 0 of R is a 0 for everything. And so this will mean that 0 of S and 0 of R are automatically the same. Now, the question is that, what about the identity? Now, not all rings have identity, but if a ring does have a multiplicative identity, if it has a 1, does that mean that, well, first of all, we call it a ring with identity. I've said that before. And if R is a ring with identity, our questions are, if you have a subring of that, will that subring have to have an identity also? Will they also have to have 1? And if so, will the 1 of it be equal to 1 of R? 1 of S will be equal to 1 of R or not? In some ways, you might think that if there's justice in the world, yes, the answer should be yes, maybe to both of these. But in fact, the answer is no to both of these. And I will give you examples to show that. And the reason is that multiplication, we haven't really have that much to work with. All we know is that we have closure and associativity, and that leaves room for lots of things. So let's look at an example. The integers is our very nice ring that we like, and multiples of 3z, when you plus or minus 0, plus or minus 3, plus or minus 6, so forth. If you look at multiples of 3, that is a subring of z. Why? Because if you add two multiples of 3, you get a multiple of 3. If you multiply two multiples of 3, you get a multiple of 3. And the negative of a multiple of 3 is a multiple of 3. Yet 1 is the identity of z, but 3z does not have a identity. There's no element no multiple of 3 that if you multiply it by other multiples of 3, you get that element back. So here's a ring with an identity, a perfectly good ring. The integer is just as good as they come, and it has a subring without an identity. But things can actually be even worse than that. So look at the ring of integers mod 6. So the elements of this ring are 0 through 5. and you add and multiply modulo 6. You add or multiply the usual way, but the answer that you really get is the remainder when you divide by 6. So in that ring, if you looked at that, that ring, that original ring, does have an identity. Its identity is 1. 1, when you multiply it by other things, nothing changes. Now look at the subset 0 and 3. Now this is a subring because 3 times 3, well, you might say 9, but when you take the remainder and divide by 6, the remainder when divided by 6, you get 3. So 3 times 3 is 3. 3 plus 3 is 0. Minus 3 is 3. This is a subring. It's a subring of R. And the 0 is the same 0 as we had noticed. But the point here is that 1 is the multiplicative identity of R, but 3 is the multiplicative identity of S. So in this case, even though the subring does have an identity, it actually has a different identity. And that's a problem. So this is a little note that you should take note of if you're going to work with rings. Now, the situation with integral domains is better. Now, the integers was an integral domain, and 3z did not have an identity. So things aren't perfect with integral domains, but much better. So what is an integral domain? Integral domain is a commutative ring with identity. So commutative means multiplication is commutative. Addition is always commutative in a ring. And it has at least 2 elements. And what that means, it has at least 2 elements. It means that it has a 0 and a 1 that are different than each other. And it has no 0 divisors. What's a 0 divisor? An element A is a 0 divisor if it's not 0, and when you multiply it by there's some other non-zero element that you multiplied by that give you 0. So if you have AB equals 0 and A and B are not 0, then both A and B are 0 divisors. Some authors have 0 itself as a 0 divisor. I don't. In integral domains, we have cancellation. That's one of the properties of integral domains that we talked about in an earlier video, the one where we defined rings and looked at their properties. In fact, all of these things were discussed there. So what does that mean? That means that if you have AB equals AC, and if A is not 0, if A is 0, well, B and C could be anything, because 0 times B equals 0 times C, no matter what B and C are. But if A is not 0, then we get B equals C. And this is even though in an integral domain, we don't have inverses necessarily. Usually in a ring or in a group, for example, if you had AB equals AC, you would conclude B equals C because you would multiply on the left by A inverse. But in an integral domain, you might not have inverses. But even though you don't have inverses, you do have cancellation. The argument for this was given in a prior video, but it's so easy that I'm going to give it to you again. So if AB equals AC, you can subtract AC from both sides and get AB minus AC equals 0. Then because of the distributive laws, we can write that as A times B minus C 0. But now we have 2 things that multiply and give you 0. Because the integral domain does not have any 0 divisors, you're not allowed to multiply 2 non-zero things to get 0. One of these must be 0. A is not, so B minus C must be 0. And if B minus C is 0, B equals C. Okay, so why am I going through this song and dance? The reason is that if you have an integral domain, and if you have a non-trivial subring of R with an identity, so I'm looking at a subring, and I'm assuming that it has an identity. I need that because I don't want to fall into the trap of 3 times Z. So as long as you have that, and as long as it's non-trivial. What does non-trivial mean? All that means is that it's not just the element 0. I want 0 and 1 to be different. Because that the 0 is a subring, and it has its own identity 0 because 0 and 1 are the same there. I don't want that situation. So as long as you have something bigger than just 0, the dull 0 subring, and it has an identity, then its identity will be the same as the identity of the big guy of the big integral domain. So in the integral domains, you're not going to have the situation that we saw with 6 mod 6z, where you have a big ring with an multiplicative identity and a subring with a multiplicative identity, but those identities are different. And again, as long as the subring is non-trivial, it's not just the 0 subring. So what's the proof of that? Well, take that one. This S was supposed to have a 1, so take its 1 and multiply it by itself. Well, you get 1. But this is also going to be the same as 1s times 1r. Why? Well, because 1r, identity of r, is an identity. And when you multiply it by something, you get that something back again. So you get 1s. But now we are in an integral domain, and s is non-trivial. And so we know that 1s is not 0. So because of that, we can use cancellation. So we can cancel the 1s on the left of 1s equals 1s, 1r. And we can do that because 1s is not 0. We know that because s is non-trivial. And when you cancel that, you get 1s equals 1r, and you're done. Okay. Last slide, I want to also say that we can define subfields the same way that we would define subrings. If you have a field, and if you have a non-empty subset of F, then K is a subfield of F if it's a field itself. What does that mean? That means that K is a subfield if, first of all, it has to have 0 and 1 in there. And for all A and B in K, A plus B, A minus B, and AB is in K. So it's closed under addition, subtraction, and multiplication, just like subrings. But moreover, if you have non-zero elements, you find their inverses, multiplicative inverses have to be in K also, which means that you can divide by non-zero elements. So so you have to have all of those. Here's an example. The rationals are a subfield of the field, the quadratic integer quadratic integer field Q joined square root of 2, and that's a subfield of the real numbers, and that's a subfield of C. Okay. Here's another example, slightly so look, let F3 be the field with 3 elements, Z mod 3Z with addition and multiplication mod n. Then look at the F3 is inside F3x, which what is that? That's the polynomials with coefficients in F3. So that's an infinite field, and not an infinite field, sorry, it's a ring. F3x is not a field, it's a ring. Actually, that's what's the point I was trying to make, because not everything has an inverse. For example, the polynomial x does not have an inverse there. So what we have is that F3 is actually a subring of this other ring, F3x. It happens to be a field. So it's a subring that's also a field. Sometimes we sort of abuse our things, and we do say that F3 is a subfield of F3x, but that's sort of in conversation that's not being precise, because the way I define subfield is that you are a subfield of a field, and this guy is a field, but it's not a sub. In this situation, it's not a subfield of a field, but a ring. So this is the end of this lecture. This was the 4th lecture on rings. It was preceded by a motivational lecture that talked about Diophantine equations and why we study rings. Then we defined rings and looked at integral domains and fields and their basic properties. Then we had examples of rings and fields. And after this, we will talk about homomorphisms and their kernels, and finally ideals. Till next time.